come poi preferisce trovarsi per un programma?
Try English.
Yeah, we try in English. If it is too much, he will switch to Italian.
So we are going to work all the time over a field K of characteristic 0.
E puoi aspettare il gesto?
Non se potevi spezzare il gesso perché faceva un po' di male.
So we are going to say something about differential reality algebras. The acronym is DGLA. So what are these? These are graded spaces over the integers. There is a differential which raises the degree by 1. There is a bracket of degree 0. This is antisymmetric in a graded sense, so where we denote by x bar the degree of the element x, and it satisfies a graded version of the Jacobi identity. And that's it. So, as a motivation, we are going to record two important applications of the DGLAs. On the one hand, we have the slogan by Deligne and others that in characteristic 0, any reasonable deformation problem is governed by a DGLA, and we are going to explain what this means. On the other hand, we have an important result by Quillen, which says that DGLA are a model for rational homotopy theory. So we are going to explain this thing. Let's here record the construction of the Deligne groupoid. So a groupoid is, we recall, is a category where all the morphisms are invertible, so are isomorphisms. Then let L be a nilpotent, or more in general, pro-nilpotent DGLA. In particular, we have the degree 0 part is an ordinary Lie algebra, an ordinary nilpotent Lie algebra, and has a group structure given by the Becker-Campbell-Hausdorff product. So we call L0 with this group structure the exponential group of L. We also have the important Maurer-Cartan equation. The set of solutions is called the Maurer-Cartan set of L. We have that the exponential group acts in a natural way on the Maurer-Cartan set. This action is called the gauge action. We denote it in this way, and it can be compactly written in the following form. Where this calculation is understood in a is made in the semi-direct product of a copy of D, and this is not important. So we have a group, an action of this group. We can construct a groupoid from this data, which is the Deligne groupoid of L. This is the groupoid whose objects are the Maurer-Cartan elements of L. And given Maurer-Cartan elements X and Y, the morphisms between these are the gauge equivalence, that is the A in L0, such that A gauge X equal Y. So this is by definition the Deligne groupoid. Let's see why this is important in deformation theory.
Maybe it could be a good idea to say what a groupoid is,
I say
No, but to say it's a category where all arrows are reversible. I mean, just
well,
the fundamental groupoid would be an example.
Of course. Well, there is a canonical way to see every group as a groupoid with only an object, and the arrows are the elements of the group, and the composition is the product of the group. So groupoid generalized group. And the fundamental example of groupoid is, like Professor Piazza was saying, the fundamental groupoid of a space. The objects are points of the space, and the arrows are homotopy classes of paths from one point of the other. And there is a good, well-defined composition. Let's go on. I'm sorry. So, deformation theory. Let's consider a typical deformation problem. We have the X, a complex variety. Complex manifold. We want to consider the infinitesimal deformations of the complex structure of X. These are, by definition, diagrams of this form. That is, we have A is an object in the category of Artinian algebra, local Artinian algebras with residue field isomorphic to C. And the typical example we want to consider is A equal Ct modulo the either generated by Tn. From a geometric point of view, A is a point. It has a scheme as only one close point, and all the other elements are to be thought as infinitesimal directions going from this point. Here we have to assume, for technical reasons, that this is a flat morphism. This is this condition means this family varies in a continuous way. We want an isomorphism between X and the geometric fiber of this morphism over the only close points. These are, by definition, infinitesimal deformations of the complex structure. there is a notion of equivalence between such deformations. Then we can construct the functor of formal moduli of X, which is a functor from the Artinian rings to groupoids. What is this functor? It sends A to the groupoid where the objects are deformations of X over spec A, and the morphisms are just the equivalence of deformations. This is obviously a groupoid. Now, what we want to say, and what does it mean to say that DGLA controls a given deformation problem? As this example was supposed to show, given a formal deformation problem, formal means we are only interested in infinitesimal deformations. Given a formal deformation problem, we can extract a functor of this form from Artinian rings to groupoid. On the other hand, given a DGLA, we can construct such a functor which sends A to the Deligne groupoid of L tensor the maximal ideal. Now, if A is Artinian, the maximal ideal is an nilpotent algebra. There is a DGLA algebra structure here given by scalar extension. And this is nilpotent, so the Deligne groupoid is well defined, and so any L define such a functor to say that the DGLA L govern a formula moduli problem seen as a functor in this way means that for all A we want an equivalence of groupoid between MA and LA. L controls M if okay. This is what it means for a DGLA to control a deformation problem, and the philosophy / theorem is that all reasonable deformation problems are controlled by a DGLA in this way. So this was the first thing we want to record. Now, on the rational homotopy theory side, we want first to recall what a simplicial set is. So, simplicial set is a diagram of this type. We have a sequence of sets x0, x1, xn. Need more space. In general, we have m plus 2 arrows going from xn plus 1 to xn, which are called the phases operators, the phase operators. And we have n plus 1 arrows going from xn to xn plus 1, which are called the generacies. These are supposed to satisfy some relations, which we are not going to write down, but we will try to explain the geometric idea behind. Now, these are purely algebraic combinatorial objects. The idea is that they model well-behaved topological spaces. So we want to explain how. Let's recall that the topological simplex, this is the set of n plus 1 in more down-to-earth words. These are for n0 we have the point, for n equal 1 we have the interval, for n equal 2 we have the triangle, for n equal 3 we have the tetrahedron, and so on. The obvious generalizations. Given a simplicial set as this, we want to construct a topological space. Now, to get the idea, it is convenient, forget about the degeneracies and only consider the phases. So what do? We take the elements of xn are called n simplexes of our simplicial set. So we take the disjunct union over all the simplexes of x of a copy of the topological simplex of the same dimension. I don't know if it's clear what we are doing.
The second union.
This is a disjunct union.
But those are two different ends. One is the natural, the other is an element in Xn, or.
This is a x.
That's an x. Okay.
Yeah. So we are just taking a disjunct union of simplexes, and then we take the quotient with respect to a certain equivalence relation. What is this equivalence relation? Less than by the face of the I fit. That's the noun by the symbol, the phase operator. The equivalence relation here is the one which identifies the copy of the n-1 simplex corresponding to the yx. It's identified with the iesimal phase of the copy of the simplex which corresponds to x. I don't know if it's.
Shouldn't I come into the notation on the right hand side?
No. No, we are here. We are.
Okay.
We are identifying this simplex with the e phase of this one. And we may do something similar with the generations and the relations which I have not written are those which tell me that this is a well-defined equivalence relation, and this pasting is coherent, and we get a well-defined topological space, in fact a CW complex. So, in other words, the idea of modeling spaces by the simplicial complexes, simplicial sets, is just an algebraization of the old idea of approximate spaces by polyhedrons, taking triangulations. So, that's it. Now, more in general, we can talk of simplicial objects in a category by taking the xn's to be objects of that category and the arrows to be morphisms of that category. We introduce the following DG algebra. These are differential graded commutative algebra of differential forms on the topological and simplex with polynomial coefficients. Now, this is a differential graded algebra. In fact, it's a differential graded subalgebra of the normal algebra over the simplex. And these differential graded algebras are arranged into a simplicial set, a simplicial differential graded algebra. Where the phases take a form on the simplex and restricted on the phase of on the if phase, I phase. Really sorry about my English. Okay. So we have this simplicial differential graded algebras. Now, let L be is a GLA. By extension of scalars, there are induced DGLA structure on these tensor products. So we have a simplicial DGLA. Now we can take Maurer-Cartan elements to get a simplicial set. We get a simplicial set which we denote by Maurer-Cartan infinity DL. Now, the fundamental result of Quillen is that if we take the category of the GLA in degrees, in non-positive degrees, in strictly negative degrees, and we localize it with respect to the class of quasi-isomorphisms. And what does this mean? It means that we take the category which we construct from this one by forcing the quasi-isomorphisms to be actual isomorphisms. So this can always be done in an abstract way by adding formal inverses, and this gives rise to a well-defined category. So there are several other ways to describe it. And we can similarly form the category obtained by the connected and simply connected topological spaces by inverting the rational homotopy equivalence. Then let's recall that given spaces x and y are rational homotopy simply connected and connected. Rational homotopy equivalence between these is an F such that it induces an isomorphism in homotopy modulo torsion and this for all n, of course, greater than 2 since we are. So these are rational homotopy equivalents. This is called the rational homotopy category, and the theorem of Quillen is that these two categories are equivalent to each other. So in this sense, we have that the GLAs are a model of rational homotopy theory. How does this correspondence works? In this direction, it follows from the Sullivan approach to rational homotopy theory, that in this direction, we take the GLA L and we send it to the rational homotopy type of the geometric realization of this Maurer-Cartan infinity. So this is what we wanted to recall about rational homotopy theory. So the subject of this talk, what we want to introduce is a function from nilpotent GLA to simplicial sets such that two things hold. For all L, we have these two simplicial sets have the same homotopy type. On the other hand, this is a generalization of the Deligne groupoid because for the GLA in non-negative degrees, I should say that these are the GLA we usually encounter in deformation theory. For such GLAs, we have that the infinity L is isomorphic to the nerve of the Deligne. We recall that the nerve of a category is the simplicial set where the n simplex are sequences of n composable arrows, and where the phases are given or by the composition of two sequent arrows, or by eliminating the first or the last one arrow. So this completely determines the groupoid, and this is what this object is what we want to introduce, define. So we are missing one thing to define such objects, which are L infinity algebras. So, an L infinity algebra is informally a DGLA where we have relaxed the Jacobi identity up to a system of coherent homotopies. So what does this mean? It means we have a differential and a bracket of as before, and this satisfies the Leibniz rule. I forgot to write the Leibniz rule when I defined the DGLA. This satisfies the Leibniz rule. For each, if we write the Jacobi identity in this form, this is no longer satisfied. We have a bracket with 3 arguments, which is totally antisymmetric in its graded antisymmetric in its arguments, and of total degree -1, such that the Jacobi identity is replaced by this one. So the Jacobi identity is satisfied only up to an homotopy given by the ternary bracket. Now the ternary bracket and the binary and the quadratic one must satisfy an Eiger-Jacobi relation up to homotopy. The homotopy is given by a bracket in 4 arguments going. So we are going in this way. We have brackets of arbitrary arity, all totally antisymmetric and of total degree Q minus n, such that the first 10 brackets satisfy a sort of Eiger-Jacobi relations up to an homotopy given by the n+1, and so on. What is the idea behind this? Is to introduce something that has the same homotopy theory of DGLAs, but is more flexible than DGLAs, and this flexibility is illustrated by the following theorem. Let's recall that if we have DG spaces a contraction between these is a diagram of this form where F and G are commute with the differential, and moreover we have that G composed. So this is the definition of a contraction. The homotopy transfer theorem tells us that if we have a contraction such as the and an L infinity structure on L, there is an induced L infinity structure on M, and an equivalence of L infinity algebras from M to L. So we apply this theorem we
Can you repeat the statement over here?
we have an L-infinity algebra.
Any.
Any algebra. We forget the Higher brackets and look it as a digispace. And we have a contraction of digispaces from L to a smaller space M. And there is a canonical way to transfer the L-infinity algebra here to the L-infinity algebra structure here to an L-infinity algebra structure on M, equivalent in an appropriate sense
to the original.
to the original one. We want to apply this in this situation. We have the forms on the n simplex with coefficients in L, and we have the integration of forms over simplexes induces a quasi-isomorphism of digispaces with a complex of non-degenerate cochains on the simplex with coefficients in L. This is the quasi-isomorphism induced by integration, and this fits into a homotopy, into a contraction. So there is an induced L-infinity algebra structure here. Okay. These L-infinity algebras fit into a simplicial L-infinity algebra. And as for the GLAs, there is a Maurer-Cartan equation for L-infinity algebra, which is the natural generalization. So we can take Maurer-Cartan elements to obtain a simplicial set, which is the simplicial set we wanted to define our Deligne groupoid of L. Now, I'm afraid let's just say two things on this simplicial set. Well, we can visualize it in a very concrete way, but I'm afraid that now this will take too much time. In low dimensions, we can look at n simplexes here as cochains with coefficients in n. So we have one cochains. So we have something like this, or like this. And these x, y, a are elements of L of the appropriate degree, and they must satisfy some relation imposed by the Maurer-Cartan equation. Here, this becomes just that x is the Maurer-Cartan elements of L. Here, this becomes the x and y are Maurer-Cartan elements. And A is a gauge equivalence between these. Here, when E equals 0, in particular, since E has to be of degree -1, this is automatically the case if L is concentrated in non-negative degrees. Here, this is an element a two simplex of the Ruggero Deligne if and only if x, y, and z are Murray-Cartan elements, A, B, C are gauge equivalents as above, and moreover we have the A, Becker-Campbell-Hausdorff, the product of Becker-Campbell-Hausdorff of A and B, this must be equal to C. So we recover the isomorphism with the nerve of the Deligne groupoid when L is concentrated in non-negative degrees. Do I have 5 minutes more? I may stop
2 or 3 minutes.
I don't know. I may also stop here.
Maybe 5 minutes would be too much. If you have some short comment, otherwise it's.
Okay, let's. Well, let's say because this is why it's interesting to consider this object, this function. Now, in deformation theory, we will skip this part because it involves passing from deformation theory to derived deformation theory, so which is the analog of classical deformation theory in derived algebraic geometry. We are going to skip this thing. Let's just say that there is a left adjoint of this function with a clear geometric interpretation. Maybe I will talk about, I don't know. With a clear geometric interpretation, okay, let's keep. Using this junction, we can do two things. The first thing is that we can prove Quillen equivalence of rational homotopy theory in just one passage, where in the Quillen approach this is proved in 4 passages, and in Sullivan approach this is proved in 2 passages with some unnecessary restrictions. So, and we can transfer the model category structure here. We can define a new model category structure here, which should give a model for the rational homotopy theory of spaces which are not necessarily connected, which was the case in the approach. So I think I'm just doing worse. I stop here.
Maybe we have time for one question before going to the roof.
I mean, I'm wondering whether there is, a geometric output, completely easy geometric output of this beautiful theory that could be explained to, a second-year undergraduate student, third year.
What do you mean by output?
Well, for example, take a very complex theory in algebraic topology, like surgery theory. There are books on surgery theory, and it's a very complicated object. But on the other hand, that if you apply surgery theory to spheres, you find I don't know how many spheres that are homeomorphic to the 7 spheres, but they are not different. Okay, this is a very easy thing that you could explain to someone third year undergraduate, because all the words are there. Right? Now, I was wondering if there are examples of very easy, very easy to state applications of this theory. Maybe, for example, deformation theory or rational multiple theory.
Deformation theory is not easy to explain the applications because they involve derived deformation theory, which is not an easy subject in itself. An application could be what are typical non-connected spaces we would like to model. For instance, mapping spaces. So we have the topological spaces X and Y, and let's suppose the Y is good, admits a localization. Let's say it's simply connected. And let's say for simplicity that X is finite. So maybe these are unnecessary, but I prefer to go on what I'm sure of. So recently there has been a lot of work into giving Lie models for the mapping spaces. If those who don't know what this is okay. Let's see with the compact open topology. So, and how can we construct a model for these mapping spaces? Well, we can do this. We can take polynomial form on X. We can take a Lie model for epsilon. There is an L such that the rational homotopy type is that of epsilon. And how we construct a model for the mapping space? Well, this is if you want a Lie model, we can just take the forms, polynomial forms on X with coefficients in L. And so maybe it's not what you had in mind.
No, okay.
It doesn't answer the question. Well, let's say that the model is given by cochains on X or force on X with coefficient in L. This is our model. And just in this. Sorry for.
Ruggero speaker.